Hello everybody, welcome to our fourth lecture, optical cavity. Now let's start this lecture, please. Okay. In the previous lectures, if you remember, we dealt with what we call Einstein coefficient. We calculate the three Einstein coefficients: the stimulated emission, the spontaneous emission, and also we calculate the absorption coefficient. We reach what we can call the central equation for laser, where we can extract the conditioning of gain, which is that the population on the energy level N2 should be greater than the population level of the energy of the first energy level N1 multiplied by G2 over G1, which is constant. Now let's turn to the next lecture, which is the optical cavity lecture. Actually, in this lecture, I will start to rotate somehow between the PowerPoint presentation, as you can see here, and also I will use the lecture script, as you can see also, because in this equation, in this lecture, we have a lot of mathematical equations. So let's now turn to the word optical cavity. What is the optical cavity? Please remember that this lecture is demonstrated in a PowerPoint presentation, in a lecture script, and also you can see it in our reference, Laser Electronics by Verdine, using chapter number 5. Optical cavity. Simply, I believe you already deal with what's called a rectangular waveguide in the microwave course in your previous semester. And you can easily represent this, you can easily represent this this rectangular waveguide by this box, which has a two-dimensional, and the wave is propagating inside this rectangular waveguide. Now, I will also close these two terminals of the waveguide, so it becomes like something like a box. Mathematically or geometrically, we can call it a cuboid. But I will make a very, very small hole so that this small hole can only penetrate, can only permit light to be inside, but it will not be able to permit light to go outside the cavity. So it will be something like that. Light can enter from this small hole, and then the light will start to make a propagation inside the cavity and return back, and so on. So we have a small hole, a very, very small hole. Its dimension is very, very small with respect to the dimension of the cavity, and we have this hole in order to allow light to be inside, and then light will propagate inside the rectangular waveguide. Now, we are now trying to mathematically express the journey of this light propagation inside the optical cavity. So let's now return to the lecture script. Okay, let's start to make it like that. This is our cavity. Now I am assuming a two-dimensional cavity. Here, the incident light, somehow this light, due to the gap, will enter the optical cavity. The light will start to propagate, and then it may somehow transmit outside the cavity. We are trying now to express this truth. First of all, please try to assume that we have light inside the cavity. It's not important where from this light comes. We already have a light. We already have an electromagnetic wave, which is called E node and H node inside the cavity. And we are now trying to write an equation to demonstrate the propagation of this electromagnetic wave inside the cavity. So, first of all, we have this E node. E node is the initial electrical field inside the cavity. As this E node propagate inside the cavity, there will be another term, I believe you know it very well, which is e power minus j k z. E power minus j k z is the propagation term, where k is the propagation constant and equals to 2 pi over lambda. So as far as the light is propagating, this E node will be multiplied by e power minus j k z, where z represents the distance moved by the wave. If we say that this cavity have a dimension of d, then when the light reaches this point, it will have an electrical field equals to E node multiplied by exponential minus j k multiplied by the distance d. So at this point, the electrical field equal E node e power minus j k d. Now, when this electrical field reaches this border, based on our knowledge from electromagnetism, from microwave, even from physics, we know that we have two possibilities. Some of this energy will be reflected and returned back, and the remaining part will be transmitted outside. Now we are more interested about the amount of energy that will reflect it back. From microwave and from electromagnetism, we know that we have a reflection coefficient called gamma. Let's say that this is gamma 2 because this is the border number 2. So at this point, which is E node minus, I call it, E node minus will be equals to what reaches here, which is E node e power minus j kd, multiplied by gamma 2, which is the reflection coefficient of the border number 2. Now, if this electromagnetic wave propagate and reach this point, then it will have an energy equals to E node multiplied by e power minus j kd and another e power minus j kd. So it will be e power minus j 2 kd, and then this is multiplied by gamma 1 due to the gamma 2, which is the reflection between border number 2. Now, this point, again, some of this energy will be reflected and some will be transmitted. And again, I am still interested in what the amount of energy being reflected. So E1 plus is equals to e power minus j 2 kd, which is a round trip 2 kd, multiplied by gamma 1 multiplied by gamma 2, which is this equation. So E1 is equals to gamma 1 times gamma 2. Gamma 2 comes from here, the reflection from this border. Gamma 1 comes from here, the reflection from the first border. And e power minus j k 2d, where 2d is the total round trip the light moved in order to make a one trip from this point till this point. So this is the first, or the electrical field after the first round trip. If I would like to write the electrical field due to the second trip, then I should expect another gamma 1, another gamma 2, and another e power minus j 2 kd. So it will something like that. E gamma 1 square, gamma 2 square, e node times e power minus j k 4d. So now you can write the electrical field of this propagating wave at any point on the cavity based on this equation. Then, as you know, or as you can understand from this e power minus j kd is simply a mathematical term. It represents a cosine and a sine function. You know basically from mathematics that e power minus jx equals to cosine x minus j sine x. So this term can fluctuate simply from 0 to 1. It's a sinusoidal signal. Its maximum value is 1. Its minimum value is 0. If this term tends to 0, that means we will not have electromagnetic propagation inside the cavity, because simply you will multiply this constant by 0, so the output will be equal to 0. And what is the condition to make this term maximum? Actually, the condition to make this term maximum is simply to have this exponential equals to 1. When this exponential is equals to 1, then this term will be a maximum term. Now, the question is, how can we make this term is equals to 1? In order to make this term is equals to 1, then you have cosine k to d. You need cosine k to d to be equals to 1. Mathematically, to have a cosine function equal to 1, you need to have the argument or the input equals to the multiple of 2 pi, because cosine 0 equals to 1, cosine 2 pi equals to 1, cosine 4 pi is equals to 1. So if this term is equals to a multiple of 2 pi, that means that this exponential term turns to 1. So now, in order to have a maximum condition inside the cavity, 2kd should be equals to q times 2 pi, where q representing an incremental integer parameter. It can be 0, 1, 2, 3, whatever. In all cases, it will lead to a multiple of q, a multiple of 2 pi. So this is a very, very, very important condition, because this condition will lead to a maximum electromagnetic field inside the optical cavity. From this condition, we can have a lot of derivation, because simply you can remove these two with these two, and then you can say that k equals 2 pi over lambda. So you can say that, or here, yeah, k equals 2 pi over lambda, but we can write it in a better format. You know that lambda is depending on the medium, so lambda simply equals to lambda naught over root epsilon r, which is n. So you can say that simply lambda equals 2 pi n over lambda naught, where n here represents the refractive index of the material, and lambda naught is the propagation inside air. So if I substitute these 2 pi n over lambda here, then I will have, I will can get this important term. That this is a condition. You can ask yourself a question here: why you are interested in d, or what is d? Let's remember, d is the distance between the two borders of the cavity. Why I'm interested in d? Because d is a design parameter. You can tune d in order to get the maximum condition. So simply, when I substitute by the term k equals to 2 pi n over lambda naught here, I can get d in one side and all other terms in one side, and then I can reach this equation, which represents that d should be equals to q, where q again is an integer, lambda naught over 2 pi. So in order to design your cavity, you should make d, which is the distance between the two borders, equals to multiple of lambda naught over 2 pi. You can make it lambda naught over 2 pi, lambda naught over pi, 2 lambda over pi, and so on. This will happen, or you will make it like that, in order to maximize the electrical field inside the cavity. Now, we can rewrite this equation in another term. In this stage, I write the equation in terms of lambda, however, in terms of q. However, I also can write it in another term. I can say that mu, which is the frequency, should be equal to qc over 2nd. What I make it here is that I substitute lambda by c over mu, and then I get all the terms in one side and the mu in another side. This is again a very important equation, because this means that the frequency propagating inside this electromagnetic optical cavity is a discrete frequency due to the term q, because q again is an integer. So you can put q equal 1, then you will have c over 2nd. You can put q equal 2, so you have 2c over 2nd, or c over nd. You can put q equal 3, then you will have 3c over 2nd. This is the frequency that can propagate. So simply, you will not be able to see a frequency equals to, for example, 1.2c over 2nd. This frequency will not exist. The only existing frequency will be the discrete frequencies related to this equation. So this equation will limit the frequency propagating, and we will say that these frequencies are an integer frequency. So as we can see, these frequencies are integers. As I just said, the first one is equal to c over 2 and d. The second is equal to 2c over 2 and d. The third is equal to 3c over 2 and d. The fourth is 4c over 2 and d, and so on. So we can here define what's called the frequency, the free spectral range. What is the free spectral range? The free spectral range is simply the distance between each two successive discrete frequencies. For example, the first one is equal to c over 2 and d when q is equal to 1. When q is equal to 2, then the second frequency will be 2c over 2 and d. If I subtract the second frequency with respect to the first frequency, this is the gap between the two successive frequencies, which is the free spectral range. And we call this free spectral range as delta mu. So delta mu, which is delta mu free spectral range, is equal to c over 2 and d. Let's now go on. Now let's turn back to the optical cavity. If you remember here, I say that the first incident light is called E node. This E node will propagate on one trip. After a one trip, E node will be E1, which is the electromagnetic field after one trip, is simply equals to gamma 1, gamma 2, a reflection between the first and the second border, multiplied by the incident, multiplied by the distance propagated, which is e power minus j k 2d. When I go to E2, which is the second trip, is simply the same first trip multiplied by gamma 1, gamma 2, e power minus j k 2d, or simply gamma 1, gamma 2 square, e node, e power minus j k 4d, and so on. So, based on that, we can write an equation in this format. Please here try to understand this equation. This equation represents the total electrical field inside the cavity. So the total electrical field is simply the summation of all these electrical fields. The initial one, after the first trip, after the second trip, after the third trip, and so on. I'm just calculating now all the electrical field propagating in the cavity. So the total electrical field is the initial electrical field, which is E node, plus the electrical field after the first trip, which is gamma 1, gamma node in gamma 1, gamma 2, E node, e power minus j k 2d after the first trip. Then the second trip, gamma 1, gamma 2 square, e node, e power minus j 4, e power minus j k 4d, and so on. So this is just a direct summation for all the electrical field inside the cavity. As you can see, simply you have an E node as a common factor in all these terms. So you can easily get E node outside as a common factor and say it's 1 plus gamma 1, gamma 2, e power minus j k 2d, and so on. This is one of the famous series, mathematical series. So you can easily say that this mathematical series, which is some mathematical issue I'm actually not so interested in, that this is equals to 1 over 1 minus gamma 1, gamma 2, e power minus j k 2d. So simply, after reaching this equation, you can say that the electrical field total is equals to E node times 1 over 1 minus gamma 1, gamma 2, e power minus j k. Okay. Now we are expressing the total electrical field traveling from M1. That's why we call it here. This is M1. That's why we are adding all these terms together so that this is the total electrical field propagating from N1. Simultaneously, we can say, or we can calculate the total electrical field propagating from M2, which is simply E naught minus and E1 minus and so on. Let's now remember that E naught minus is equals to E naught multiplied by E power minus j k d, because it's a single half trip, and then multiplied by gamma 2. And then in E node minus E1 minus E node 1 minus, which is here, it will be equals to 1d, 2d, 3d, so e power minus j k 3d multiplied by gamma 1, or gamma 2 first, gamma 1, gamma 2, so gamma 2 square and gamma 1, and of course the initial one, which is E naught. So simply, in order to write the electrical field propagating from the second mirror, you can say simply that this is equals to E total minus equals to E naught gamma 2 e power minus j k d, the first term, then gamma 2 square, gamma 1 E naught e power minus j k 3d plus and so on. Again, you can have this whole term as a common factor. And then you will have 1 plus gamma 1 gamma 2 e power minus j k d plus and so on, which is typically the same like the above series. And then you can say that the Et minus is equal to E naught gamma 2 e power minus j k d over 1 minus gamma 1 gamma 2 e power minus j k d. This is the E total minus. So the total intensity, or if you would like to calculate the intensity, if you remember the intensity, or what you can call in microwave or in electromagnetism, I believe you call this the Poynting vector S, which is 1 over 2 eta multiplies by E squared, if you remember the Poynting vector. So this is what we do it here. The intensity equal 1 over 2 eta multiplied by Et plus square. Or you can make it the same with Et minus, as you like. So that's why I use the term plus here to indicate the intensity of the electromagnetic field coming from mirror number 1. You can simply calculate I1 minus as Et minus times Et minus over 2 eta again. And eta, if you remember, this is the impedance of the medium, which is, I believe, root 120 by in case of propagating in air, if you remember. So here we can easily calculate it by getting the square of this term, or actually to be more mathematically right, we can get the term multiplied by its complex conjugate, if you remember. So now we are going to calculate this intensity. The mathematical steps in between are not required. Then if you calculate the intensity, I plus will be equals to E naught square over 2 eta, 1 over 1 minus root R1 R2 square plus 4 root R1 R2 sine square kd. What is R1 and R2? R1 and R2 is simply gamma 1 square and gamma 2 square. This is a very, 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 very important conceptual point. Because when you are going to say gamma, and when you are going to say R, gamma is a reflection, and R also is a reflection. But gamma is a reflection from an electrical field point of view. So when you have an electrical field propagating here, then the amount of electrical field reflected at these points equals to gamma 2 multiplied by the incident electrical field. So now gamma represents the amount of reflected electrical field. But when we are talking about power or intensity, which is proportional to the electrical field square, as I just mentioned, then the reflected power from this point is equals to R multiplied by the incident. So simply R is gamma square. So when we are dealing with electrical field, the reflection is represented in gamma. When we are dealing with power or intensity, the reflection is described in terms of gamma square or in terms of R. So simply R1 and R2 are gamma 1 square and gamma 2 square. So now we reach this very, very, very important equation. This equation represents the intensity of light, or the intensity of electromagnetic wave, which is in our case light, that will be propagating from the first mirror, and it's now given in terms of R1 and R2, which is gamma 1 square and gamma 2 square, and in terms of K and D, which is the propagation constant and the distance between the two mirrors. Now let's continue. So now, what about what is I node? Let's now return back to the optical camera. If you remember, in the beginning of the lecture, I told you that the energy propagating here is starting with this E node. And I told you, please don't ask where this E node comes from. We will answer this question later on. Now, E node is the initial energy on the first starting point of the optical cavity. So what about the intensity? E node is an electrical field. Then what is the intensity? The intensity is simply E node square over 2 gamma. So the intensity of the first initial electromagnetic field just after the border of the cavity can be represented by the term I node, where I node is equals to E node square over T2 Very simple. Now let's return back to the optical cavity. Now actually, let's now return back to the question. Where E nodes come from? In order to have an E node inside the optical cavity, which is here, you should have an incident electromagnetic field. This incident electromagnetic field will somehow enter the cavity, and then you will have E node. If there is no electromagnetic field outside, of course there will be no electromagnetic field inside. Then, if I told you that we have an intensity called I node here, then this I node comes from another I in, or incident intensity here. And basically, as we described, when the electrical field E incident reaches this border from the outside border, it has two probabilities. Some of this electrical field will be reflected in this direction back, and of course I'm not interested in it, and another will be incident or transmitted. And again, based on our description, we just say that the amount of reflected energy is equals to gamma times the incident. So if this E is incident, then the amount of reflected energy in this direction, in the negative acceleration, let's say, is equals to gamma 1 multiplied by E incident. This is the energy that will transmit. And accordingly, for the power, if the power or the intensity coming here is equal to I incident, then the amount of intensity reflected back will be equals to R times I incident. If R times I incident will reflect, then how amount of energy will transmit? Simply 1 minus R1 times the I incident. So, for example, if I say that this border will reflect 70% of the energy, then you will say, okay, the incident will 0.7 of the incident will be reflected. Then 0.3 of the incident will be transmitted, which is 1 minus the reflected amount. So we can simply say that the amount of energy inside the cavity, the first amount of energy inside the cavity, the first intensity amount inside the cavity, which is I node, is equals to 1 minus R1 times I in. I in, the incident energy, R times R in will be reflected, and 1 minus R times I in will be transmitted, which is I node. So I node is equals to 1 minus R1 times I in. Very perfect. Now, let's turn to another issue. What about the transmitted energy? Oh, what do you mean by transmitted? Let's now return to the cavity. So, as you can see here, this light is propagating like that. And in the first description, I usually tell you, please, I'm interested on the reflected part, not in the transmitted part. That's why when we reach this point, we multiply it by gamma 1, which is the amount of electrical field reflected here. And again, here's gamma 2 and so on. So what about the amount of light transmitted there? It's simply what is coming from here multiplied by 1 minus R2. Because what will be reflected is simply R2 times the intensity coming from here. So what is transmitted is simply the 1 minus R2. Again, let's say the same example. If I say that this mirror has a reflection of 60%, then 60% of the light will be reflected back in the negative x direction. And 40% of the light, which is 1 minus 60%, will be transmitted to the right-hand side of the cavity. So in order to express the amount of energy transmitted in the cavity, you can simply say that the intensity transmitted is the incident intensity coming from the first mirror or the first border multiplied by 1 minus R2. Very simple like that. Okay, we already know that I1 plus, we already calculated here. That's right. This is I1 plus, as we calculated. Then the I transmitted is 1 minus R2 multiplied by I plus. 1 minus R2 multiplied by this term. That's great. But let's now write it here. I think we will find it here somewhere. Yeah, so this is, let's stop here. Okay, so this one is typically what I say. This 1 minus R2 multiplied by the previously calculated I1 plus or I plus. Sorry. But let's now try to see. Oh, E naught square over 2 gamma is simply the I naught. And I naught is equal to 1 minus R1 times I in. So I can simply remove E naught square over 2 gamma or 2 eta, sorry, E naught square over 2 eta, this term can be simply removed, and I can put 1 minus R1 times I in. So I can say like that the I transmitted equals to 1 minus R2, 1 minus R1 times I in times this huge mathematical term. Now, I have the transmitted intensity in one side, and I have the incident intensity in the other side. So I can say, or I can now calculate the transmission as the transmitted power over the incident power. Very simple. If you have a glass, and I say that, oh, I am incident intensity equal 100, and the transmitted is equal 50, then how much of light is transmitted? Oh, simply it's 50 over 100, which is 0.5%. So that amount of transmission is simply equals to I transmitted over I incident. So this is the transmission equation. Now we reach a very, 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 very important equation. I believe if you check my exams, in-class tests or final exam during the previous 3 years, you will typically find this equation in the final exam or the in-class. Because this is a very fundamental equation in order to describe the output. Again, I will never ask you to memorize this equation. However, I will usually ask you to understand this equation. And now what we are going to do is we are going to try to understand the equation. Now, let's somehow simplify this equation. How can we simplify this equation? We have in this equation 4 unknowns. R1, which is the reflection from the first border, R2, which is the reflection from the second border, or simply matter. We call it matter because we are reflecting light. So this is a reflection from the first light mirror. This is a reflection from the second mirror, R1 and R2. And we have K, which is the propagation coefficient, equals to 2 pi n over lambda naught. And we have D, which is the distance between each two successive, or each two, sorry, the distance between the two mirrors. So this is the input. In order to reduce these 3 parameters, or sorry, in order to reduce these 4 parameters into 3 parameters, we can simply say that R1 is equal to R2 equals to R. We can assume that we have 2 symmetrically or 200% matched mirrors. R1 is equals to 2, R2 is equals to R. And another very important issue. Now you are trying to maximize the transmission. That's true. So what if, or what should we do you do in this term to maximize the condition? Let's see. What is the maximum transmission? Theoretically, the maximum transmission is equal to 1. What? All the light incident will be transmitted. No light will be reflected. So the maximum here is equal to 1. Let's say if R1 is equal to R2, I'm sorry, this one of course is dummy one, has no meaning. If R1 is equal to R2, then this is 1 minus R, then here in the denominator you will have 1 minus R whole square. What is about the denominator? Here R1 is equal to R2, so this is R1 or R square under root, which is R, so you have 1 minus R all square plus 4 R sine square KD. Then what is the condition to take this t equals to 1? Simply, if this term is equal to 0, then you will have 1 minus R square over 1 minus R square. That's right. So you should act to make this term is equal to 0. Very simple. So how should I make this term is equal to 0? Simply if this sign is equal to 0, because no way to have R equal to 0. The only way is to have the sign is equal to 0. And how can I make sign equal to 0? Simply if you can put this term as a multiple of pi, because sine 0 equals to 0, sine pi is equal to 0, sine 2 pi is equal to 0, and so on. So if kd equals to q pi, then this term is equal to 0. Please try to memorize this equation, and let's now return back here. Do you remember this condition? It is typically the same. 2kd equal q2 pi. This is the condition we extracted from the electromagnetic wave here, if you remember. So if you make kd equal q pi, then you will have maximum electrical field inside the cavity. Now, okay, let's now here again, it's typically the same condition. If kd equal q pi, then this t will equal to 1. So what are the conditions? Simply, if I got you this equation and I told you what are the conditions in order to make this transmission is maximum, then you should have two conditions. First, the two mirrors should be symmetric, should be matched, should have the same R. Then the k times d should be equals to q times pi. These are the conditions for a maximum transmission. Now, let's now reach to one of the very important points of this lecture. Let's now return to this equation. I believe this equation we previously learned, that the amount of light transmitted, I transmitted, equals to 1 minus R2 times I incident. If you remember, let's now return to the cavity here. The amount of light transmitted here is equals to the amount of light incident here multiplied by minus 1 minus R. The example when I say to you, if 60% of the light is reflected, then 40% of the light will be transmitted. Very simple like that. So this is an equation we already understand somehow, that the transmitted light is equal to the incident propagating light multiplied by 1 minus R2. Okay, then you can say that one minus R2 I plus over I trans. Okay, I think there is some error in this equation somehow. Okay. We can make it. We can make it from scratch. So this is the first equation. That's right. And also we have the equation that and also we have the equations that this is the I transmitted. That's right. And we have the equation that the transmission is equals to 1 if R1 equals R2 equals R, and KD equal Q bar. So simply I can substitute this I transmitted by this term. So 1 minus R2 I plus over I incident, here just I substitute this line instead of I transmitted is equals to 1 if these two conditions occurs. Then that means that I plus is equals to I incident 1 over 1 minus R2. Okay, very simple mathematical equation. 4 steps mathematical equation. First, I start with T equals to 1. Then I transmitted over I incident equals to 1. I transmitted is equals to 1 minus R2 times I plus. Then you 1 minus R2 times I plus equal I incident. Then I plus equal I incident over 1 minus R2. Where is the issue? Where is the point? Now let's see this point. These are mirrors. And as you know, mirrors are perfect reflectors. So, because when you stand in front of a mirror, you see your image. It's 100% reflection. Okay, let's say it's not 100%. Let's say it's 99% reflection. So that means simply that if R here equal 99%, which is 0.99, that means that I plus equal I incident over 1 minus 0.99, which means that I plus equals to I incident over 0.01. That means that the running wave inside the cavity can be much larger than the outside, including the used exciting cavity. I mean here that the light propagating inside the cavity is 100% times the incident. So you can simply have one intensity of, for example, 5 photons per meter square incident, and you can have an propagating field which is 500 photons per meter inside. This is simply the equation. So you can create a very large input using a very small, sorry, you can creating a very large output or a very large propagation based on a very small input signal. Now we define what's the term, the quality factor, or Q. Simply the Q is the ratio between Q node, mu node, which is the central frequency you are propagating, over delta mu, which is the full width half max. Please don't be confused. We define in the beginning of the lecture, we define a term called delta mu. This delta mu is the free spectral range. So usually in the exam, I would like to use delta mu, and here you can find Fs or free spectrum to indicate that this is a delta mu free spectral range. However, in this case, delta mu is equal to the full width half maximum, which is the same you use in communication. Here, as I mentioned, the revision is not required, so you can simply say that delta mu full width half maximum is equal to C over 2 and D 1 minus R1 over 2 over R1 over R2 to the fourth root. This equation will be given to you. So simply, if I told you to calculate the quality factor, the Q is equal to the central frequency over the full width at half maximum, which is this term. Finally, the end of this part of the lecture, I will describe something called the fins or F. The fins of the signal or F if the speed is a free spectral range over the full width or half maximum. This delta mu is the full width at half maximum, and this again, and this delta mu is the free spectral range. So if you divide the free spectral range over the full width at half maximum, you will get the fins. Finally, I would like to show you a very important graph. Okay, of course we make this step by step somehow. This transformation equation. This is a very important graph. This is the transmission T versus the Q times versus the Q, which is the integer value. I mean, let's make it like that. So this is the condition here. Yeah, this is Q. So again, when Q is equal to integers, Q is equal to pi, or 2 pi, or 3 pi, or something like that, you can say that the transmission is equal to 1. So here you can see that T equals to 1 if and only if Q is equals to pi. Now, this is also another some other equation. Now, the second condition is, what is 0.7, 0.8, 0.9? This is simply the reflection, the R. What are the value of this R? Or what are the value of this R? So the reflection is simply represented by R. If you can have R 0.9, 0.7, 0.8, so for each value of R, you will have a different value or a different curve. Again, this is also an important curve. Most probably, I will ask you in the exam to sketch such a curve. So you have to know basically how you should sketch such a curve. Okay, so now this is the end of this part. I will try to make this part also. I will try to make also a recording for a example, a mathematical example where you can solve step by step in this part. It will be also an important example. It's, I think, a question we inserted in a final exam, or in the previous year final exam. So it will be an helpful example for you, where you will ask to determine the T, determine the conditions, determine every and each step of what we did. So I think this will be somehow helpful for you. Finally, thank you for your concentration, and let's meet in the next part of the lecture, part number 2 again, about the optical cavity. But in this case, we will start discuss something called the photon lifetime. This will be the point for the second part of the lecture. Thank you very much for your concentration, and see you in the next.